Thank you, Kyle, for the invitation to come up and talk to everybody. I'm just going to use my professor voice, as I say, and not use the microphone. So if you can't hear me from the back of the room, raise your hand, yell at me, that's okay. I'm going to try and make this a little interactive at parts. I want the young people in the room to shout out answers and a couple questions I'll throw at the crowd. And I'm not actually going to talk anything about biology, so Kyle's introduction was all wrong. That's what I do in my day job. This is my evening job, to do science during Eclipse events. I'm a faculty member in chemical engineering, as Kyle mentioned in the introduction, but I also have the distinct pleasure of running the NASA Idaho Space Grant Consortium. So the NASA Idaho Space Grant Consortium is actually a over $1 million program that NASA funds through the University of Idaho to help inspire kids to go into STEM-based careers. And so that's how Kyle got introduced to myself and our organization, because really it's the kids in the room that we're trying to inspire to make sure that we really do get to Mars like NASA wants to do. Because I'm not going to be alive when it happens, I'm too old for that. So I have that pleasure of running that program. We send funding throughout the state of Idaho to communities, to libraries, to public schools, to private schools, to teachers, and so that's something that I like to give a plug for, and you can see why we have a great synergy with SpacePoint and their desires to really help make NASA and space a focus here in the Sandpoint area. So, what is a solar eclipse? Does any of the little people know?
A solar eclipse is when the sun and the moon line up. And when you're on Earth, you just see, like, the Earth can see, like, the sun look kind of darker.
Okay. So why does it get a little bit darker? And we got this great animation from NASA. It's because when a solar eclipse happens, the moon, as was said, you were 100% correct, is in between the sun and the Earth. And it's actually the shadow of the moon that creates the eclipse effect. So I thought it would also be important to talk about the scale of these planetary bodies. And so we have a diagram here that I borrowed from another organization. You're going to see all my slides I borrowed from other people. And this shows you the scale of teeny tiny planet Earth in front of the sun. So planet Earth is actually really, really small compared to the size of the sun. And then the moon is even smaller than planet Earth. And so the moon is about 4 times smaller than the planet Earth. And it is located way away from the planet. So you can imagine that being able to get that shadow from this teeny tiny marble that's flying around a slightly bigger but teeny tiny marble to give you a shadow from a giant ball of flaming gas is a pretty unique event. So what happens when we get this shadow effect is the shadow really will depend on where you are located relative to the shadow and the alignment of the sun, the moon, and the Earth. And so many people will end up only seeing a partial eclipse during solar eclipse events because they're outside of that area where the specific shadow ball is traveling across the United States or somewhere in the world. But another important question is, why don't we have solar eclipses every month? The moon goes around Earth every month. We see all of the phases of the moon every month. Why don't we get an eclipse every month?
Is it because the Earth is moving too?
Yeah, the Earth is moving in one way, the moon is moving in another way, and so sometimes, you know, the shadow might be on a different part of the planet. Sometimes the moon may not be in alignment between the sun and the Earth, and the shadow might just go off into space. And so it could be too high above the Earth, it could be too low below the Earth, and we only get a solar eclipse event when we get a perfect alignment and the moon lines up with that line of the light coming from the sun onto planet Earth. So when we have an eclipse, in the science world, we like to think about 5 different phases of a solar eclipse. So the first phase is where the shadow first starts to go into the visible spectrum. It just starts to cover part of the sun. And that's what we call the first contact of a solar eclipse. The second contact point is when we get the full solar eclipse event to begin, and we go through what's known as totality. And the thing about the upcoming total solar eclipse in April 2024 is there will be over 4 minutes of totality, which is a pretty awesome thing for us to experience. And when you're under totality, a lot of really cool things happen here on planet Earth. After the moon shadow continues to move on, you'll go through the third contact where totality ends, and ultimately the eclipse event will end at fourth contact when the moon completes its movement across the face of the sun. So we also have a very unique experience to see an annular solar eclipse this coming October. So an annular solar eclipse happens when the sun is too big and the moon will not completely cover it. So does that mean that the moon is closer to the sun or further from the sun? We got closer. We got closer. We got further. Further. Okay, so we're in a tie. Who's the tiebreaker? Tiebreaker vote? Closer. Okay, so what happens is the moon is actually further from the Earth, and so we get an interesting crossing of the light from either side of the moon, and we get to see what's known as a ring of fire. So when the moon is over the sun and is blocking most of the sun, there's a ring of light that will still be visible around the exterior of that shadow. So here's a map of the solar eclipse event that is this coming October 14th in 2023. And what you'll see is the path of the annular solar eclipse goes through southern Oregon, through Utah, New Mexico, out of the United States through Texas. But you'll also notice that everywhere across the United States, you'll be able to see some level of that shadow. So you won't be right on the perfect shadow dot, but you'll be in a part of the country where you'll get a partial solar eclipse. So even up here in Sandpoint, even if you don't travel anywhere, you'll have greater than 70% of the sun covered by the shadow during this solar eclipse event. And in April of 2024, we will have a total solar eclipse that actually goes the opposite direction across the United States. It goes through Texas again and continues up and goes out through Maine, leaving the United States. And so this is, as was mentioned in your introduction, going to be the last solar eclipse event that crosses North America for 20 years. So it's a pretty cool opportunity for us to go do some really interesting science. Again, though, you can see the lines, and it may be a little hard to read the numbers, but there will be part of this solar eclipse visible everywhere in the United States again. So again, up in Sandpoint, we'll be on the order of 30% of coverage of the sun during the eclipse event if you're unable to travel. So still something that's really cool for all of you to experience and get to see. So it's also, though, extremely important to be safe when viewing solar eclipse events. And so I have to put in my safety plug from NASA. You see, I stole this slide straight from NASA because I don't want to get blamed. But I will say that at the back of the room, I have brought eclipse glasses for everyone who came here tonight. You're free to take a pair. You can probably even bring a pair home for your friends and family. I brought 200 pairs, and I don't need to bring any of them home with me. But you'll need to wear these eclipse glasses if you want to look at the sun during the eclipse events. Even during totality in the annular solar eclipse event, because there's that ring of fire that is outside that can really do some damage to your eyes. So please, they'll be in the back of the room. Take a couple sets for you and your families to use during these eclipse events so that you can look and see this amazing opportunity that we have. NASA NASA is doing a ton of events related to the solar eclipse, and I'll transition into some of the stuff that I'll be doing during the solar eclipse events in just a second. But I wanted to put up this QR code. You can sign up for NASA's newsletter. They will send you emails about all of their events. They will keep you informed about where they'll have viewing parties, where they'll have resources. They have all sorts of amazing materials about eclipses if you want to dive into some of the other science that NASA and NASA-related people are doing. But I'm here to talk to you also about the nationwide eclipse ballooning project. And I'm one of the project leads on this nationwide eclipse ballooning project. We are essentially a university-based citizen science project to take measurements during both solar eclipse events. Our eclipse ballooning project is composed of 2 tracks within our program. We have one side of our program where we will be doing atmospheric science measurements during the solar eclipse event. We will be launching these little sensors called radiosondes that are used by the National Weather Service. And we are going to launch them once an hour for 30 straight hours, 24 hours before the eclipse, during the eclipse, and 6 hours after the eclipse. The other half of our project teams are on the engineering track, and it's kind of funny that I'm an engineer, but I'm on the atmospheric science side. They will be building a larger balloon payload where they're going to send up cameras along with a number of instruments to take atmospheric measurements. And they're actually going to do a live stream video feed for NASA, and they're going to send the video feed from balloon team to balloon team to balloon team so that we can watch the eclipse go across the United States. All right, so why do we care about eclipses? Eclipses are a unique opportunity for us to have a very short duration where we lose all of the energy that the sun is putting onto the earth. So it is essentially a living laboratory for us. A lot of really cool things happen during an eclipse. All of the animals go dead silent. The atmosphere calms down. And it essentially does the exact same thing that the atmosphere does during the evening hours when everything calms down, except that it does it over a very short duration of time. Totality is 4.5 minutes for the April eclipse event, and that is actually a very long totality. So we'll have 4.5 minutes to take measurements and see how much the sun impacts the earth. So you can imagine we have, instead of our normal full day of sunlight, we have a little blip where we have this very intense shadow go across the earth and change all of the interactions on our atmosphere. So here's an example of some of the measurements that we'll be taking. This is the solar radiation hitting the surface of the earth at a solar eclipse event. And what you see is that when we get that first contact point of the eclipse event, the solar irradiation, the solar energy that's hitting the earth starts to go down. And there are some strange spikes. Why do you think there's some strange spikes in this data?
Because the atmosphere is changing because of the shadow.
Okay, so the atmosphere is changing for the shadow, so that's the big spike. What do we think these separate little small spikes are? Okay, so it's not what we use to record the data. Good guess. So what floats through the sky every now and then with lots of sunlight? A cloud. So these are what happens when a cloud goes through. It also blocks the sunlight. It reduces the energy, but usually it's for a much shorter time period. And even when a cloud goes overhead, it doesn't block all of the energy. When we have an eclipse event, it blocks all of the energy, and our solar irradiance goes all the way down to 0. All right, so this is what happens to the temperature on the surface of Earth when we undergo an eclipse event. Again, we see when we have that first contact point, we don't have much change because it takes a little while to block enough sunlight to change the temperature. But we then see a dip in the temperature because things get colder. We don't have all of that energy hitting the Earth. But what you might notice is that the lowest temperature point does not match up with totality. And that's because there's a delay in when you lose all that energy. There's still some energy that comes off of the Earth from before, and there's a delay to allow everything to normalize. So that's due to the energy that the surface of the Earth stores from the sunlight. All right, so this one's a hard one. So this is relative humidity. And luckily we all live here in the Northwest where we don't have a lot of humidity. But you can imagine if you lived in the Midwest and South where it's really humid. And during an eclipse event, humidity goes up right after totality. And that's because of the change in temperature in the atmosphere. And so there's an inverse relationship for humidity, or the amount of moisture that is held in the air. And lastly, I said that when you have this eclipse event, everything calms down on Earth. So what we see, this is a measurement of wind blowing on the surface of the Earth at this location. And you can see there's all sorts of wind, and it's going up and down and gusty and breezy. And we have the solar eclipse event, and all of the winds calm down. And that's again because we lose all of that energy, and everything in the atmosphere starts to calm down, and we then lose the winds that are blowing across the surface of the Earth. So there's a lot of really interesting things going on in the atmosphere during these solar eclipse events. So what my research group and the research groups as part of the Nationwide Eclipse Ballooning Project are doing is we are actually attempting to measure what is known as an atmospheric gravity wave. Who's heard of that? Nobody, exactly. Oh, a couple people. All right. This is not a gravitational wave. We are not looking for the space-time continuum. An atmospheric gravity wave is what happens in the air when you throw a rock in a lake. You see waves, right? So in the atmosphere, when you take away the heat, it creates waves. It creates ripples because you lose temperature and the atmosphere wants to normalize. And again, if we have just a spot, a shadow of the moon where we lose that energy, it creates ripples going out from that location. Atmospheric gravity waves happen for a number of different things. They happen off of Schweitzer Mountain. And when you see these beautiful cloud patterns where the clouds are lined up, that's a signal that there's an atmospheric gravity wave going through that layer of cloud coverage because it has a nice wave-like pattern, and that impacts what happens to the clouds. So since only 2 people raised their hand to say, yes, I've actually heard of this phenomenon, why do we care? So atmospheric gravity waves and our ability to quantify them and measure them and understand them better will help us improve our ability to do weather forecasting. So they're a very important energy transfer process in the atmosphere. And all of our models of what happens and all of the models that are used to predict weather going into next week, and we all know we look on our phone app and we look at the weather next week. I don't believe what it's going to say, right? It's going to be totally different by the time we get there. We can help improve those forecasts to give us a better prediction of weather. All right, so how are we going to measure these atmospheric gravity waves, these ripples in the air? We launch high-altitude weather balloons. We launch the same weather balloons that the National Weather Service launches twice a day. This is the exact same instrument that the National Weather Service launches twice a day, and they get this data and feed it into their models. And we're going to launch these weather balloons for 24 hours leading up to the eclipse and 6 hours after the eclipse. And what these little instruments do is they give us temperature, pressure, GPS measurements, which we can use to get wind speed and direction. And they'll allow us to do some analysis to see if we find an atmospheric gravity wave. So our high altitude balloon payloads are about a 5-6 foot in diameter balloon when we're at the ground level. We fill it with helium gas to get a lift. We have a parachute and then down to our payload. And who wants to guess why we have a parachute?
In case the balloon pops.
Okay.
So the payload doesn't shatter.
Awesome. So you are absolutely correct. So we include a parachute because these balloons rise through the atmosphere. And ultimately, we get to about 100,000 feet in the air and the balloon will pop. And then our payload will come all the way back down to Earth. And on the engineering side of our nationwide Eclipse ballooning project, the student teams will go out and track down their payload, recover their cameras and sensors and data. We can go try and track down our sensors, but you can imagine these are pretty hard to find, especially in the wheat fields of the pollutes. All right, so as our balloon rises up through the atmosphere does a number of different things, and we collect all of this data going up to about 35 kilometers, so about twice as high as airplanes fly. And we will collect, like I said, temperature and pressure and wind speed and direction. While we go all the way up to the atmosphere, our balloon will pop, and then we can collect all of the data back down to Earth as well. So I want to show you an example launch, and because I'm a UI person, we had to, of course, recruit Joe Vandal to our ballooning team. So this will show you some of the steps for doing a balloon launch. 3, 2, 1, rock. So we were told that Joe Vanna could even come do our field campaigns with us when we go to the Eclipse events. I don't know if Joe's actually going to travel. We'll see. So this is another cool video. This shows what happens when our balloons reach their peak altitude. It's pretty impressive to see what these gigantic balloons do when they decide to finally pop. So they just basically disintegrate. And they're actually designed to do that. And you can see this was from one of our collaborating teams. This was a larger payload that had a camera on it, so that they can get these really awesome videos on their payload until their parachute deploys, and then it floats back down to Earth and they recover. Those flyers. Right, so. But of course, we get to do these balloon launches in all sorts of crazy conditions. I had the pleasure of traveling during the pandemic to Chile to see a total solar eclipse down there. And I think a lot of people in the room have heard when the atmospheric rivers line up and hammer California with all of the rain. Well, when we were in Chile, an atmospheric river aligned with our total solar eclipse. But that didn't stop us from launching our balloons. We still launched all of our balloons. This next video I like to show because it's pretty funny. This was not actually in Chile, this was in Oklahoma. And you can imagine in Oklahoma there are days where it's just really, really windy. So this is an example of a funny extreme launch. So Joe Vandal had a pretty easy launch, right? These guys are a little harder on this one. All right, so that's our atmospheric side of our nationwide eclipse ballooning project. Like I mentioned, there's also an engineering track where they're going to do the larger payloads. And as I mentioned, they're going to send up cameras that are connected to satellites. And they're going to do a satellite relay of a live feed of the eclipse shadow crossing the United States. They're also including instruments. They are also trying to detect the atmospheric gravity waves. But they're also going to do this great public outreach on behalf of NASA so that the entire country can appreciate the eclipse event even if you aren't able to travel to it. All right, so for the annular solar eclipse in October, this map shows where all of our project teams are going to be located across the United States. So all of the little blue dots are teams doing the same science that I'm doing, our 30 balloon launches over 30 hours. The orange dots are the teams that are doing an engineering payload that will pass that live video stream as the eclipse takes place. And my team and Joe Vandal will be here in Lakeview, Oregon, doing our eclipse event and interfacing with the local middle school and high school down there to excite the kids there to go into STEM-based careers and understand what's happening with this really cool annular solar eclipse event. And as soon as this eclipse event is done, our project will put up the map of where all these teams will be for the total solar eclipse as well. So this is just one more really cool picture taken from one of these high altitude weather balloons. I thought it would be a great way to transition to, a website if you want to learn more about our nationwide eclipse ballooning project. As I mentioned, we have on the order of 35 universities, community colleges, tribal colleges across the country that are working on this project so that we can collect this citizen science type level of data over these eclipse events. And I always have to do an acknowledgement slide because we have project funding from NASA and the National Science Foundation that helps support these efforts, and a number of amazing students, primarily undergraduates, who have helped me do these projects. So for the middle-aged kids in the room, think about getting involved on projects like this as soon as you can. Think about doing rocket launches because we can collect really cool data with rocket launches also. So that's all I have in terms of eclipses, and I would be happy to take any questions that anyone might have.
Is the bluish purple ring around the Earth the stratosphere and the mesosphere?
In the video or in the picture? Yeah. So the question was, is the bluish haze the stratosphere? I am guessing that is probably higher up than the stratosphere because it's looking out over the Earth. But you are correct, it is one of the layers of the atmosphere. That's a tough question. No hard questions, it's Saturday. How do I predict when a solar eclipse is going to happen? So there are some people who are a lot smarter than me, and they do mathematics, and they can calculate and predict the path of the moon around the Earth and the Earth around the sun, and so they do the math to calculate when the eclipse events will actually happen.
How easy is it to find out, like, for this gateway for the spring, how easy will it be to find out, like, where some of Europe and other parts of the world? Like, what other resources do you go to?
So it does not actually go into Europe. Most eclipse events have a shorter path. They don't go all the way around the Earth. And that's actually why eclipse events over land are fairly rare. They often happen over water because they don't cover the entire thing. But NASA has some resources that do where the path is. The maps that I had a couple slides back that show the percent coverage in various locations. These are all generated and are publicly available and can extend, if you're maybe down in South America or the Caribbean or something.
So when you mentioned that this is the last one for 20 years, you meant in North America?
Yes, in North America. Yes.
How often does balloons get hit by planes?
That is an awesome question. I have never had one get hit by a plane. So before we do campaigns like this and before my team does practice launches, we actually submit paperwork called a notice to airmen. And we send it to the FAA and they distribute it to any planes that have a flight path in the region. We actually do some calculations to estimate where the balloon is going to go for every single launch. And we send that information as well, and so they pass the information on.
Even to small people below like 2-person planes?
Yes, so it is available at the airports depending on the magnitude of the airport you are in. So we do a lot of practice launches in Moscow, Idaho, and we used to call the regional airport, and they finally said, stop calling us, it's okay. Because really it's just, if a plane is going through, they are very visible, they're very large objects, and they have a pretty straight line trajectory. So we have not had any interactions with planes.
Can you tell us again how high the balloons go, and then how long does it take to get to the point where they explode? And I'm guessing it depends on whether it's small or large.
Yeah, so the balloons that we launch are, they're referred to as 600-gram balloons, so that's the weight of the balloon before we add helium. Ours go to about 35 kilometers or 100,000 feet, and it takes them about 2 hours to get that up. They come down a lot faster than they go up. So lunar eclipses are very similar. A lunar eclipse is the shadow of the Earth on the moon. Right? So if you think to the solar eclipse is the sun and then the moon and then the Earth. A lunar eclipse is the sun and then the Earth and then the moon.
So it happens on different sides of the Earth.
Yes.
Have you ever had a balloon land in water?
So luckily, see, this is why even though I'm an engineer, I do the atmospheric science track. I don't have to go find these. I get all of my data through a radio transmitter, so I don't have to worry about it. We put stickers on them to ask if anyone finds them, that they can send them back. There's actually a website that shows every one of these that's in the air around the world on any given day. So if people go out and try and find them as hobbies, and then they send them back to us. Luckily, I have never had to go swimming for a payload because I'm not a swimmer. So yes, so ours have a GPS sensor in them, and it sends the GPS location by radio transmitter. For the bigger payloads, they often have multiple trackers. They have a satellite tracker, a GPS tracker, and sometimes a radio tracker. In the back,
When is the next lunar eclipse?
I honestly do not know.
Who analyzes the data?
So the data that we collect, my students and I analyze it. The data that the National Weather Service balloons collect, they give it to the forecasters, and they use it in their models to help give you better weather predictions for all of our great phone apps.
What is the gas in the water?
So we fill our balloons with helium. But the challenge is helium is getting really hard to find right now. And so you can imagine if we have all of these things across the country, how hard it is to find all of that helium so we can all launch our balloons. You can also do the same thing with hydrogen gas, but hydrogen gas is a little more dangerous. And so we really try to use helium when we can.
And the weather balloon goes high as a kite.
It goes higher than a kite. It goes higher than an airplane flies.
How much helium do you guys put into your balloons?
Okay, so we actually do some calculations to figure out exactly, because it depends on the temperature of a given day when we do our launch. But we put in about 400 psi of helium in one of our balloons.
If we put hydrogen in your balloon and it's hot, does hydrogen from the sun and smoke, doesn't it kind of put you in the sun?
Well, the problem with hydrogen is it's really, really flammable. So you have danger if there's a spark, you can have a really big fireball, which is what the sun is. A solar eclipse can absolutely happen on other planets, because I am sure that at some point, for example, Earth goes between the sun and Earth and Jupiter, right? So we create a shadow also. So I am sure that solar eclipse events happen on all of the planets that are on the outer side. Just the most inside one probably doesn't get it.
I just wanted to point out that eclipses are how we look for other planets outside of the solar system in a way, as we look for the little blip that goes in front of stars.
Yes,
Sorry,
absolutely.
I'm a nerd.
No, you're 100% correct. That's just not something I do, so I try not to give the hard signs.
How long does it take for a lunar eclipse to happen?
It takes, for these solar eclipses to happen, it takes from first contact to fourth contact. It takes a couple hours.
400 psi.
Yes.
How thick is the material?
It's actually not that thick. They're kind of like the balloons you used to be able to go get at your grocery store. It's a little thicker than that, but they're just latex balloons that we use.
How do moon glow?
How does a balloon glow?
No.
The moon? The sunlight off of the surface of the moon.
Is there anybody tracking or capturing any data over water? So you mentioned, a lot of it's out in the valley.
To the best of my knowledge, no. But we did even think about trying to do that in 2020 because of the pandemic. So we had a team of 4 universities that were going to do these balloon measurements across South America in 2020. We were going to have 2 sites in Chile and 2 in Argentina. And then the global pandemic hit and Argentina completely shut down and Chile shut down and then reopened and then shut down and then reopened. And so we were panicked that we wouldn't be able to go to our data. We actually had negotiations ongoing with the US Navy to try and launch from a vessel in the ocean outside of Chile. Thankfully, they decided to let us into the country because the Navy eventually said, we can't really reposition our assets for that.
This is probably a bit outside of your wheelhouse, but during these both solar and lunar eclipses, is there any noticeable tidal effect? Because you have the gravity forces aligned, same way you have physically aligned.
You are absolutely correct. That is outside of my wheelhouse. So anything I say is 100% speculation. It has nothing to do with the University of Idaho or NASA. No. I honestly do not know.
I can answer that. I can go a little bit into this. The answer is no, not really. You'll see, so the tidal waves, they have a really long period. Right, tides, they happen on such large scales that even if you have the tide of both the sun and the moon lining up, it doesn't compare perfectly. And wind effects, they will wash it out.
Thank you.
So if something happened, it would affect the waves, yes, but nothing has happened to cause it to shift it in our modern era. Something that could happen would be if a big asteroid hit the moon, would move it off of its track. NASA just did a really cool mission where we impacted an asteroid with a spaceship, and it caused the asteroid to shift which direction it was flying. So if something really big hit the moon, it could move it off of its track. The moon does not have poles. So it changes how big the shadow is, right? And so it's actually the moon going in one of its orbits where it's a little further out that we get the annular eclipse. And when it's a little further in, it probably gets a bigger shadow spot through the opposite idea. So it changes how big and how widespread the eclipse can be seen.
How do you prepare for differences in weather level? How do you do the same experiment no matter what the weather is?
We do the exact same experiment no matter what the weather is, except there's one condition you're not allowed to launch during, and that is light. Everything else we launch, we just dress formally or dress less formally, or so when we were in Chile with the atmospheric river, we launched in downpouring rain for the rain lasted about 8 straight hours, and we launched a balloon an hour in the pouring rain. I got 2 who like to ask questions. I'll get yours in a second. Do you have one?
Since you said that when it has solar, it has the wave comes down. If there were to be a tornado in the path of it, would it stop the tornado?
It would help calm down that weather. Yes. Whether it would completely shut down a tornado, I don't know. Hopefully that never happens.
That's kind of a related question. So when you were there in Chile, when you got to totality, the weather was damaging down
So the weather did calm down a little. It's kept raining. And in all of our data analysis after the fact, which we're still doing because it was such a complex set of data, we believe that the atmospheric Mystic River actually had more of an impact on the mixing and all of the dynamics and interactions in the atmosphere than the eclipse did. So the loss of that solar energy wasn't enough because of the power of the jet stream.
Okay.
Yeah, I had a question that was stolen, so.
Okay, that's the one.
Basically, I was gonna ask about like storms.
So-
I was gonna ask about storms in general. Like, what do you pass through a storm?
Yeah, so with that same idea, it depends on the strength of the storm band as it's coming through. If it's a smaller band, then it could calm it down, but if it's a very high energy band storms, then it's probably more, because of the length of time the solar eclipse is so short.
You know, what they do,
I do not have a number offhand, no. All right.
So when the moon's spring, so the light of the sun, it goes around of the moon.
So the moon is spinning us, but one side of the moon that's facing us is the side that would hit the reflection of the sunlight.
You mentioned earlier that the animals go like dead silent. Have you guys researched why that happens during the solar eclipse?
So they believe that happens because the animals think it's nighttime and they're supposed to go to bed. Right? Just like it's almost nighttime here and I have to go to bed. So that's why they think the birds get quiet, because the birds think that it's going into the evening time and nighttime, because you're losing all of the light, so it's getting darker and darker and darker. So they calm down to prepare for sleep.
They wanted to add one thing. So reducers, I lived in Hawaii, all the mine birds, all the birds, big eclipse there. Because when I were there, the birds were just yelling in their hidden position. Then it got quieter, it got dark. But then they got loud.
As soon as the light comes back, they start.
Yeah. They have no lights, they just follow the light.
Yeah.
It's very fascinating.
How do you know the exact, so like, you know the date and stuff, but how do you know the time?
So it all goes into the same calculations of knowing exactly where the moon's position is and the sun, and they can then do the math that says this is exactly where the shadow is going to be at this location, so they can tell us in advance.
What was the first recorded solar eclipse?
The first recorded solar eclipse, I have no idea. A long time ago, because I imagine there's probably stuff in ancient writings that talk about this phenomenon of a solar eclipse event, and I can imagine some ancient religions probably had, events where they wrote about it and it became part of their faith.
So like on a planet with more moons than us, say like maybe Jupiter, could you have like a double or triple eclipse to make it look like a face, or is the sun too small by the time you get so far out there that like you can't have more moons covering it than one?
I imagine that, it's probably a lot more rare, because you have to get that perfect alignment of multiple moons and the sun and the planet, but it's not out of the realm of possibility.
I have seen several through a telescope. So when we go downstairs, I'm going to show you guys the telescope. One of those I've used to observe multiple double solar eclipses on Jupiter, where you see two of Jupiter's moons, their shadows passing across Jupiter. Because Jupiter's got 4 moons that orbit way closer to it than ours does to us, and because Jupiter's so much bigger, it's really easy to see that they happen very frequently. I mean, we weren't even trying to observe. We just were out there one night and there's 2 shadows on that.
So see, that means all of the hard questions now go to the back. All right.
Is it possible that, for example, like Titan, for example, would it be able to have a solar eclipse?
All right, so what I'm going to say is, don't forget to grab solar eclipse glasses in the back. I am happy to hang out and answer more questions, but I know there's more programming to go, so I don't want to stand up here and answer questions all night, because I don't want to steal from the smarter people in the room who know much more about these things. So grab some Eclipse glasses, and if you have any other questions, come up and ask me after everyone's filing out.